A famous mathematician, Euler, some of you might have heard of him, he came up with different types of circuits and paths. There is a difference between a circuit and a path, but we'll get to that first. So Euler wanted to go on a graph and wanted to only cross the edge once. Only wanted to cross an edge once and get to every vertex on our vertex edge graph. So every vertex. Okay, and this is all without lifting your pencil. Sometimes on the back of cereal boxes, they'll have these things and you'll have to look at it and try to figure out if you can go from one point to the next without lifting your pencil and reach all of them and whatnot. So you can only cross an edge once, you can't lift up your pencil, and you have to get to every vertex. So for instance, all right, so I have to, by get to every vertex, that doesn't mean that you can't go to a vertex twice. Okay, you just can only get to every edge once. So we'll talk about Hamilton paths tomorrow, and that's where you can only cross the vertex once. So with this being said, I'm going to look at this and I'm going to see if I can, in fact, create an Euler path. So I'm going to start at A. I'm going to go to A to B to C to D to E, back up to B. Okay, so looking at this one, I can't quite make it. So let me try something else. Let's start at F. Okay, I'm going to start at F. I'm going to go up to B. I'm going to go back down to F. I'm going to go to E, then up to B, to C, to D, then back to E. So in this one, I did in fact have an Euler path. I crossed every edge once. I went to a couple vertices a couple different times. Okay, so that would be considered an Euler path. So an Euler path does not matter where you start and end. Okay, so if you wanted to actually write down what we did here, we went F to A to B, back to F to E to B to C to D, and then back to E. That was our whole path. Okay? Now, as you can probably guess, if the path does not matter where you start and end, a circuit does. Okay, an Euler circuit. Euler, we know has the same conditions. We have to cross an edge once and only once. An Euler circuit has to start and end at the same point. Sorry, I'm just looking at things to make sure that they work out. There is a secret to this, which we'll get to. All right. So with this, I'm going to try this starting at A. All right, here we go. A to B to C. Okay, I know that if I come back down, that's okay, because I've still got AG open. Okay, then I'm going to go over to F, up to E, to D, to C, back to E, back to G, back to AG. So this one is in fact an Euler circuit. All right, so retracing our steps here. We went to A, to B, to C, to G, then we went to F, E, C, D, E, G, A. So we started at A and we ended at A. It did in fact work. Did anyone notice anything? There are some tricks of the trade. So I'm going to write some numbers in here, and you guys might figure it out right away, maybe not. All right, so for A, I'm going to write down 2, B is 2, C is 4, D is 2, E is 4, F is 2, G is 4. So what do those numbers mean? Those are how many edges are coming out of each vertex. Notice they're all even. Okay, let's go back here. A has 2, B has 4, C has 2, D has 2, E has 3, F has 3. As I'm writing the letter E. Okay, so we got some odds there. And then we've got all evens here. And we tried using a circuit on that last one. So here's what actually happens. In order for it to be a circuit, all vertices must be even. So you don't even have to really try to find the path. You know right now, you can just count it up and see if my vertices are even. If they're not, it's not a circuit. With a path. We're actually going to look at one more example. All right, looking at this. I've got 2, 3, 3, 3, 2, 5. Okay, so it might be a path, it might not be. All right, let's start at B. I go to B to A to F, back there. Okay, didn't work. Let's undo that. Let's try a new one. Let's try a different point. Oh no, I can't get either back there again. Okay, there is a trick. An Euler path can only contain two odd vertices. In order to make a true Euler path, you must start at an odd vertice. Something to notice, when you have to start at an odd vertice and your ending spot will be at the other odd vertex. All right, so with that being said, I've got one problem for you and I want you to figure out if it's a circuit path or none. So go ahead and figure it out. All right, looking at this, I'm not going to try to trace my steps. I've got 3, 3, 2, 2, 2, and 2. Because I've got two odds, I know that this is an Euler path. Next question. Based on this same picture, if I start at A, where must I end? Going back to our vertices here, if I start at A, that's my odd, I have to end at the other odd. So my answer then is B.